Hello students, welcome back to our lecture of second law of thermodynamics. In the previous lecture, we have covered all the topics of second law of thermodynamics, which includes the statement, Carnot cycle, Carnot theorem, concept of entropy, entropy as a function of volume, pressure and temperature, entropy changes during the physical processes, and entropy change in ideal gases and mixing of gases. So let's first revise all the formulas which we have studied in this chapter so that we can do the numerical based on these formulas. First, efficiency of Carnot cycle, which was represented by eta. Formula is T2 minus T1 divided by T2. It is also equals to Q2 minus Q1 divided by Q2. Second, entropy of fusion. Delta SF is equals to delta HF divided by TF. Next, entropy of vaporization. Delta SV, delta HV divided by TB, where delta HB, V is the latent heat of vaporization and TB is the boiling point. Next, entropy of transition. So delta S transition is equals to delta H transition divided by the temperature T. T is the transition temperature. Entropy as a function of temperature and volume. So for the N moles, the delta S entropy change is your NCV ln T2 by T1 plus NR ln V2 by V1, where CV is your heat capacity at constant volume. Next, entropy as a function of temperature and pressure. That is, delta S is equals to NCP ln T2 by T1 plus NR ln P1 by P2, where Cp is your heat capacity at constant pressure. Next, entropy change of an ideal gas during the different processes. So first, if we are taking during the isothermal process in which temperature is kept constant. So T1 will be equals to T2 and the formula will left with delta S is equals to R ln V2 by V1. It is also equals to R ln P1 by P2 in terms of volume or in terms of pressure. Second, for isobaric process in which pressure is kept constant. So delta S is equals to Cp ln T2 by T1. Third, in isochoric process, delta S is equals to Cv ln T2 by T1. Isochoric process in which volume is kept constant. Next, entropy change on mixing of ideal gases. So the formula is delta S mixing is equals to minus of R summation of Ni multiplied with ln Xi, where Ni is the number of moles of that particular component and Xi is the mole fraction. And if you want to calculate it for 1 mole of a gas, then delta S mixing will be equals to minus of R. The formula will be divided by the total number of moles. So it will become minus of R summation Xi ln Xi. Now the formula is totally completely in terms of mole fraction. Now let us do the numericals based on the formulas. First question. Calculate the maximum efficiency of an engine operating between 220 degrees Celsius and 125 degrees Celsius. Clear? So we are given with the two temperatures, initial and the final. We know the formula of efficiency eta is your T2 minus T1 divided by T2. As we know, the temperatures are taken into the Kelvin. So, adding the temperatures with 273 degrees Celsius, it will become 125 plus 273, that is equals to 398 Kelvin. Similarly, 220 plus 273, that is your 493 Kelvin. So eta will be T2 minus T1 divided by T2 on calculating, which is equals to 19.26%. Correct? Let us see the next numerical. What percent T1 is of T2 for a heat engine having efficiency 20%? Very nice question. What percent T1 is of T2? We have to calculate the percent here in which the efficiency given is 20%. So again applying the formula of eta, T2 minus T1 divided by T2. On dividing, we are getting 1 minus T1 by T2. Clear? So now putting the value of efficiency, that is 20%, 20 by 100, it will be 0.2. Taking 1 to the other side, it will become 1 minus 0.2. To make it the percentage, multiplying it with 100 on both sides. So we get the ratio of T1 by T2, that is your 80%. So T1 is 80% of T2. Right? Let's take the next numerical. Next question is, 2 moles of an ideal monoatomic gas undergoes expansion reversibly from a temperature of 398 Kelvin and a pressure of 3 bar to a temperature of 298 Kelvin and the pressure is 1 bar. Calculate delta S for the process. Assume that Cp is your 5 by 2 R. Clear? The moles, initial moles are given are 2 moles. We are given the value of Cp. We are given the value of initial temperature and pressure and final temperature and pressure. So now using the expression delta S is equals to NCp ln T2 by T1 plus NR ln P1 by P2. To convert the natural log to the log base 10, we will multiply the equation with 2.303. So it will become 2.303 NCp log T2 by T1 plus 2.303 NR log P1 by P2. We are given all the data. So in putting the values and using the logarithmic expressions, we can get the value of delta S. So in this question, the delta S calculated is 6.78 joule per Kelvin. Have a look on the calculations. Now let's move to the next example. Next question is, calculate the entropy change when 2 moles of an ideal gas expands reversibly from an ideal volume of 1 liter to a final volume of 10 liters at 298 Kelvin. So here also the initial volume and the final volume is given. But now in this process, the temperature is kept constant, T1 is equals to T2. So using the expression for the isothermal, the formula will reduce to nR ln V2 by V1. To make it to the natural log, multiplying it with 2.303 and finally putting the values. We are using the value of R as 8.314 joule per Kelvin per mole. Now the next example. Calculate the entropy change accompanying mixing of 2 moles of helium and 3 moles of neon at 25 degrees Celsius. It is assumed that the gases behave ideally. Right? Here we want to calculate the total entropy change. We are not calculating it for the 1 mole. So for the total entropy change, the formula is minus of R N1 ln X1 plus N2 ln X2. We have reduced the formula, change it with the log to the base 10. We have the value of number of moles here. N1 is your 2 moles. Kindly notice N2 is your 3 moles, right? So we have calculated the mole fractions accordingly. X1 and X2, we know that X1, the mole fraction of any component 1 is the number of moles of that component divided by the total number of moles. Similarly, X2, using the R as 8.314 joule per Kelvin per mole, we have calculated the delta S mixing. So the delta S mixing is 27.99 joule per Kelvin. This is some few examples we have discussed of this chapter. Thank you students, we have completed our first unit of second law of thermodynamics. Have a nice day.